All right, guys, let's talk about another naming system for binary ionic compounds. At this point, you're really good at naming compounds that come from the first, second, 13th columns combined with elements from the 15th, 16th, and 17th columns on the periodic table. And so here's what I'm talking about. You guys are pretty good at taking a ion that with a +1 oxidation state and combining it over here with one of our negative oxidation states like -3, for example. But there's a whole bunch of metals in the middle of the periodic table that also ionize by losing electrons. The problem with these guys in the middle, which we call the transition metals, is that they have what I like to call multiple personalities. They don't oxidize with a real consistent oxidation state like these other columns do. They're always positive numbers because they lose electrons, but they could be +1, +2, +3, all within the same element. And here's that. Metals in the center have multiple oxidation states. So here's what I'm talking about. So here's just a few examples that live here in this transition metal group. Copper, for example, will oxidize with a +1, +2, or +3 oxidation state. Manganese has a whole bunch, all the way up to +7, and iron has multiple oxidation states too. And that's just 3 examples from the, whatever there are, like 30 elements in this transition metal block. They all have multiple personalities, and so because of that, we have to name them a little bit differently. So let's take a look at some of that stuff. In the name of a compound containing a transition metal, we need to use a Roman numeral to specify the metal's oxidation state. We really only do this in the name of the compound, not really so much in the formula of the compound, and I'll show you why that's the case. And so every name of a compound containing one of these transition metals, you'll see a Roman numeral in parentheses, and I'll show you. So here's why we need these. Iron oxide, if we just wanted to put together the formula for iron oxide, the way that we would do this is to say, well, let's look at the oxidation states of both of our ions, and if they match, we don't have to do anything, we can just smush the symbols together. But if they don't match, then we have to follow our switcheroo rule. And so we don't really know, because iron is in that transition metal group, we don't really know what its oxidation state is. That's a question mark. We know the oxygen is always -2. That's in that column from the periodic table, but iron is a little bit different. So here's what we do. If we're given the name iron with a Roman numeral 3 oxide, then we know that the oxidation state of iron is +3. Now we have everything we need to do to do our switcheroo rule, and we can make a valid formula. And I just chose iron 3 oxide. This could have just as easily been iron 2 oxide or iron 1 oxide. So you'll be given in the name what the oxidation state is. And so that Roman numeral 3, that's what indicates that +3 oxidation state on the iron. See how that works? So let's go from formulas to names. I think this is actually harder to do than just taking the name and making a formula. You have everything that you need to make a formula as long as you have that Roman numeral. The anion, or the back side of the chemical formula, this is going to come from either the periodic table, or it's going to come from your list of polyatomic ions, so you know what the oxidation state is of the second part of the formula. So, but when you have the formula and then you need to figure out the names, that's a little more challenging. But it just takes some practice. So let's do some practice here. So here's a chemical formula that involves copper and phosphorus, okay? And we know that the subscripts in a formula result from the switcheroo rule, right? We know that the 2 must have been the oxidation state for copper, and the 3 is the oxidation state for phosphorus. And so when you have a formula, just work backwards and say, well, that 2 must have come from the oxidation state of copper, okay? And the 3 we know is the oxidation state of, oops, that's a minus, sorry, minus 3 of phosphorus. And so we can just work backwards and come up with the name. So if we're gonna name this compound based on the formula, we would call this copper. My C is a little weird here. Copper, and then you use the Roman numeral that represents the oxidation state here, which is a positive 2. So we put our Roman numeral 2 in parentheses, like so, and then phosphide. See how easy that is? It's no big deal. Let's do a couple more just to get the hang of it here. So here's one. This involves the use of a polyatomic ion, and so it's actually good practice here because you get in the swing of using Roman numerals, and then you might use them when you don't need to. And so aluminum, if you remember, aluminum lives in this positive 3 column right here. Aluminum sits right here. And so it doesn't need a Roman numeral because it's got a very consistent oxidation state. So this one we would just call aluminum nitrate. And so we don't need the Roman numeral because aluminum is not a transition metal, okay? But now here's one that we do. And this has a polyatomic ion as well. This is nickel sulfate. And this is a kind of a tough one for kids because you gotta remember that these polyatomic ions may be subscripted themselves. And that doesn't necessarily mean that the 4 is in any way related to the nickel here. The formula for sulfate is SO4. And so you just got to get good at looking at these polyatomic ions and know where the subscripts are coming from. Remember that if the polyatomic ion is subscripted with some outside subscript, then that would be the result coming from the nickel oxidation number. But it doesn't. This 2 is representing the negative 2 oxidation state of sulfate. And then out here, we don't see an outside subscript, so we're going to just call it a 1, right? And that 1 then is the oxidation state for nickel. And so this is nickel 1 sulfate, right? And I think that's challenging for kids because, that 4, it seems like you'd put that as the oxidation state of nickel, but just learn your formulas for those polyatomic ions. You'll be glad that you did. Here's one, iron oxide. We need to name this with a Roman numeral because iron is in the transition metal group. So let's take a look and see where these subscripts are coming from. The 2 is the oxidation number for oxygen, and the 3 must be this positive 3 from the iron. So this is iron 3 oxide. Okay, and so remember, backwards switcheroo to figure out the oxidation numbers, and then Roman numerals in a name indicate the oxidation state of the metal. Okay, and then one more thing I guess I'll leave you with is that there are a couple of exceptions to that in this transition metal group. Not, I know I said that every single one of these has multiple oxidation numbers, but there's a couple that don't. And it's confusing because sometimes you'll see a name where the metal comes from this group of metals and there's no Roman numeral. That's because it's a known oxidation number. And so the ones in my opinion, the ones to really remember are silver, which is always +1, always. And so a lot of times you'll see, silver nitrate, for example, as a name of a compound. And you'll notice that there's no Roman numeral here, and that's just because, for the same reason that we wouldn't use a Roman numeral for one of these +1 ions, we also don't use it for silver because it's always +1. Another very common one that I think you should be aware of is zinc, which is always +2. And so again, like if you see zinc chloride, for example, you'll notice there's no Roman numeral in this name, and that's because zinc oxidizes with the same oxidation state as these +2 ions, and we don't use a Roman numeral for them either. And I guess if there's one more I would point out, it's probably cadmium. We don't see this too often, but cadmium is also a +2, and so you won't see cadmium in a name with a Roman numeral. All right, so that's the way stock system of naming works, and I hope that helps you.